Hello guys, today in this video we are talking about Kirchoffs law, right? So what is Kirchoffs law and how you will use this Kirchoffs law while solving problems related to current, voltage and resistance. So Kirchoffs law, the first law, which is also known as the KCL, Kirchoffs Current Law, you can call it KCL, or also it is known as junction law. So let us see what do you mean by Kirchhoff's current law, KCL or junction law. So suppose in any circuit, okay, you have a junction. Junction means all the wires, connecting wires are connected, okay, linked. That is what is a junction, right? So at any junction, suppose I will show you currents entering. Some currents are entering here, you can see at this point, and some are leaving, right, leaving the junction, right? Some current components are leaving the circuit, suppose this, right? And we will just name it randomly, okay? For example, suppose this is the junction we said where all the wires are connected, right? And we will say this is I1, this is I2, this is I3. So these are the current component, you can see inward, incoming, and the black ones you can see they are going out of the junction. So we can similarly suppose name it I4, I5 and I6 this way, right? So Kirchhoff's current law says that the sum of all these current at a junction will be zero. Okay, so what do you mean by that actually? Okay, let us write sum of all the current, okay, sum over I is equal to 0, right? That means if you will take all the currents here and will add them, it should be 0. So all the incoming currents, like here you can see I1, I2 and I3, okay, are considered to be positive. So I will write I1 plus I2 plus I3, they are positive, and all the outgoing currents, as you can see, outgoing, okay, is going away, from the junction. So I4, I5 and I6, so those are considered to be negative. So minus I4, you can see, minus I5, and then minus I6, okay. So this is the total combination of all the currents at this particular junction A, suppose I will write. So okay, so we can write it further, I1 plus I2 plus I3 is equal to I4 plus I5 plus I6, this way. Okay, so this whole thing is equal to 0, so I forgot. Sum over I is 0, so this whole thing I considered the incoming current to be positive, the outgoing current to be negative, and sum of all the currents will be 0, so that we can write this. So incoming current must be equal to the outgoing current. This is Kirchhoff's current law, right? And we will see later how this KCL can be used to solve problems. Okay, then let's move to the second law, which is KVL, we call Kirchoffs Voltage Law, KVL, and also known as loop law. So if you write Kirchoff's second law, which is also known as KVL, K for Kirchoff's Voltage Law, or also known as loop law, right? So in a circuit we can apply it to a loop, right? A closing loop, a closed circuit, we can apply this KVL to that. Okay, so what this second law says, sum over all the EMFs, okay, that is there in the closed loop, okay, in a conducting circuit, must be equal to sum over the potential drop across each electrical components. Okay, so if every electrical component will have some resistance, you can consider resistor or any other electric component which is having resistance. So sum over E is equal to sum over IR. This gives you the potential drop across the resistor. So This is the potential drop across the resistors. So sum of all the potential drops taken together must be equal to what? The sum of the EMFs that is used in that particular loop. So sum of EMFs is equal to sum of potential drop across the resistor. Let us draw some some random circuit, and we will see how we can use this KVL, Kirchoffs Voltage Law, to that. Okay, so let us take one example here. For example, okay, let me just show you one random circuit diagram, then you will see what is Kirchoffs Voltage Law. What does it mean? Okay, let me just draw some random circuit. For example, okay, let me draw this way. Cell, positive terminal, negative terminal, okay, and then some random resistor, circuit symbol of a resistor you can see here. Now let us draw this way, and then I will connect to some random cell again, right? We'll connect it this way. Then again from these 2 points, let us use some other 2 resistors. You can see I am drawing the circuit symbols for 2 more resistors, and then let us connect it, and then let us give some random values to these resistors as well as these 2 EMFs. Okay, suppose I will give this 9 volt and will give this 3 volt. Okay, so these 2 EMFs you can see. Resistor, suppose I will give this 4 ohm, and this is 2 ohm, and this is 3 ohm, right? So these are the resistance values. You can see this circuit diagram, right? Now let us find out what is the current across each resistor. Okay, across each resistor using this KVL. So Kirchoffs voltage law we are going to use, and then we need to find out what is the current across each resistor. So let me tell you few assumptions that we need to take in KVL, right? Different textbooks, different resources, if you see, you will see like no different set of assumptions, but they are all correct. They give you the same correct answer. But you need to understand what is the logic behind different assumptions that we consider in physics, right? So here let me just tell you what are the assumptions that we are considering before solving any such problem using KVL. So the first thing is, when you are considering negative potential, negative to positive you are moving. So negative potential is the low potential. Here you can see this is the low potential. Positive potential is the high potential, right? So if you are moving from low to high potential in a loop, okay, in a loop, we will name the loop like suppose I will name it like A, B, and this is C and D. You can see one loop I consider, right? Similarly, we can just consider C, D, and then E, F, whatever order you can take. There is no restriction to the order that you are naming it or that you are referring to in any circuit diagram. It is up to you, right? But suppose you are moving from A to B here, then in the battery you are moving from low to high potential, right? So low potential to high potential, if the direction is low to high potential, there is a potential gain. Okay, potential gain, low to high potential gain, and hence we will consider the EMF to be positive. EMF is considered to be positive. This is the assumption we said, right? And then the second thing is, if you assume direction of the current, suppose I started from here, I considered the current to be I. So this I amount of current is okay passing through this 4 ohm resistor, right? And my loop is named as A B C D. This is the loop A B C D. So if in we are talking about the loop A B C D, okay, so this loop, okay, loop law, as we said, it can also be named as. So you are moving from A to B. I amount of current is passing through 4 ohm. So my assumed loop is A to B, and the current direction also I consider from A to B. So if they are same, so what I said, the second point that we need to understand, focus on, assumed path and the direction of current flow. Direction of current flow are same, then the potential drop you consider to be positive. Potential drop is considered to be positive. That means here, as we consider the current to be I, okay, and the resistance to be 4, so 4I, that is I times R, gives you the potential drop. So V1, if V1 is the potential drop over here, V1 is equal to 4 times I here. Okay, so this will be considered to be positive, and here we said the EMF is already considered to be positive because it's moving from low to high. So this way you can consider how many loops, and then you solve it, you will be able to find out the unknown, whatever is unknown. Okay, so now here in this case, as I said, EMF is equal to 9 volt. Okay, so that is only, you can see 9 volt, and then this here you got 4 times I, then you follow the loop this way, right, and then you came this way. So this is your first loop, right? So in this first loop you write the net EMF, right, sum over the EMFs. So we got 9 volt, negative, low to high. Again in this direction you got low to high, it's moving, right? So this will also be plus. So we can write using KVL, as we said, sum over E is equal to sum over IR. Sum over IR gives you the potential drop across the resistor. Sum over E gives you the net EMF. So here net EMF, this is positive low to high, this is positive low to high, 9 plus 3, 12 volt. So I can write 12 volt, okay, or simply just 12 volt is equal to, now the potential drop, you can see in this loop you have only one resistor, right, and you consider that I amount of current is flowing through this, right, so 4 times I. So I got this to be 4I is equal to 12, so I got I is equal to 12 by 4, that gives us 3 ampere current. Yeah, so I got the current flowing through this resistor. Now suppose, so same I over here you got, and then here you can see, suppose I1 amount current entered, so here you can write I minus I1, or else you can write I2, whatever we want to write, that is up to you. Okay, so if I write I1 here, I can simply write I minus I1, and then accordingly I can consider, or you take I2, and then if you will consider I2, you need to take the third equation. Like here, you consider this to be the junction. You can see I is entering, I1 and I2 are leaving. You can see from this junction, I1 is leaving the junction, I2 is leaving the junction, I is entering the junction. So the third equation that you got is I is equal to I1 plus I2. Okay, so you need to write the equations and solve it, then you can find out the unknown. So I value is already determined, that is 3 ampere here. Okay, so we got I1 plus I2 is equal to 3, right? This is what we got. Okay, let us, so we have I value. Now let us find out I1 and I2. Come move to the second loop, right? So the second loop is this one here. Here is the second loop. Suppose I will move in this way, C, D, E, F. You can take the opposite, D, C, F, E. Let us take C, D, E, F, right? That's my loop, chosen loop. Now I will see the direction of the current, okay, here for the second loop. Direction of the current for the second loop. So here if you see, you are moving from low to high. So we have, this is positive, low to high potential. So we have 3 is equal to, now you can see the direction of the current here. Okay, you can see what is the amount of current that is actually passing through 2 and 3, right? So here I1 will go this way and it came this way. Then I2 will enter here through the register, then will go, and then you got I1 plus I2. I will again flow through the horizontal. This is what our distribution of current we have considered. Okay, so now here we got the 3 volt, that is low to high and considered positive. Then I2 amount of current here is actually entering through the register 2 and 3, right? So we can write I2 and then multiplied with 2, I2 and multiplied with 3. So the same amount of current is flowing. You can see they are in series. So simply it gives you 2I2 plus 3I2, that is 5 times I2. So you can obtain I2 equals to 3 divided by 5 ampere. You got this? I2 is 3 by 5 ampere. So you can find out I1 now. So I1, as you have taken here from KCL, okay, from the Kirchoffs Current Law, for a junction we got I is equal to I1 plus I2, right? So we can write I1 is equal to I minus I2. So I minus I2, you have already obtained I value. So 3 ampere minus 3 by 5 ampere. So you write this, we got okay, here we got, you can see that this is the current direction, you can see, I mean passing from 2 and then 3, but the loop here, I forgot to write the loop here. The loop here we considered is, you can see, C, D, E, F, because 3 volt low to high I considered. So C, D, E, F we took, right? C, D, E, F loop. Now our current is in this direction. You can see the current is in this direction, but the loop we considered is in this direction, C, D, E, F, right? So we need to consider these to be negative as per the assumptions we have taken. So this should be minus 5 by 2. In both the cases the direction is opposite, so minus 5 by 2. So we got a minus sign. See, negative sign is important here. This gives you what is the actual direction of the current. Whether if you got a plus sign, okay, in your calculation, that means the assumed value and the obtained value are the same and your assumed value is correct. Suppose I considered the I2 in this direction, but in the calculation I got minus 3 by 5. That means the actual direction of I2 will be upward in this direction. Okay, so that gives you a clear idea of the flow of current. Also, when I said flow of current, we have considered the conventional current flow of positive charge. You can see that from the positive terminal we said. Anyways, so I minus I2, now it will be 3 plus, because 3 minus 3 by 5, which will be 3 plus 3 by 5. That gives you 15 plus 3, 18 divided by 5, right, ampere. So here this way we can calculate all these unknown currents. Okay, so quickly some other random example for KVL. Suppose we will draw something like this. Okay, so take this and then connect it to a register, and then this here we will make it like this. Okay, some random circuit diagrams I am drawing. Okay, then this, and you want to add EMFs or not, up to you. So suppose I'm just writing random values. 12 volt given, and here suppose I will take a 4 ohm, and this is a 3 ohm, and this is a 2 ohm, okay, register, and you find the current like across each register. If I want to find out the same way, here you can take any loop. For example, here we have 3 loops. You can see actually one can be considered this way. See the arrow marks, this one, okay, and then this one loop you can consider this way. The other loop you can consider, if you will erase this, will not consider this one, okay, and we'll consider like uh, the current will suppose follow this path, right, this and then this and then this, right, that also can be considered one loop. And then the third one you can consider this, the inside one, okay, this square one, this rectangle one, you can take that, right. So three you can use three loops you have, or else you can use like one KCL and two loops. So number of unknowns and number of equations must be the same to solve the unknown, okay. So what we will do here, let us take suppose I amount of current, okay, passing through this, then it will pass through this 4 ohm resistor and will come here, and then it will be distributed. For example, here it will like take this as I1, and then here you take this to be I2, right. So you get this and then this and then this here again I. So let us you can just name it. For example, I will name it as A, B, C, D, E, F, G, G and H, something like this. You can see the cycle. So A, B, C, D, E, F, G, H, A. The inner loop, you see this inner loop, okay, goes like this, and then this, then this. This is the loop. Okay, let us write KVL for that. Okay, so we have in this loop you are moving from low to high potential. So let us take this to be 12. Okay, positive I took, low to high I considered positive, and my assumed path is A to B, so same I took positive. I amount of current passing through 4, so I will write this to be 4 times I. Okay, then I kept B, C, D, E. Then here you can see I1 amount of current is passing through 3 ohm, so I will write 3 times I1, right. Then you can see E to F, G, H and then A. So there is no more resistor, no more EMF, only one EMF I considered. I got equation 1, right. Similarly, if you want to write the second equation, you can similarly go like A, B, again the same thing, A to B you got 12. Okay, again you got this 4I because A to B is still there. And suppose you are like moving from D to this through this, and then G through this out one, you can see there is one resistor, I2 amount of current is passing through this. So we can write your assumed direction is C, D and then G. So in the same direction, so I will take it as positive 2 times I2. You got the second equation. So you got I1, I2, 3 unknown, and the third equation you can use, which is I is equal to I1 plus I2, right? This is the third equation. So you can solve these 3 equations. Another fourth equation can also be written, but it is of no use. I mean, you can use it. Any set of 3 equations is needed. For example, for this one, the small one you will write. Okay, and suppose you are moving from D, E, F, G and then D. So if your loop is this, you consider this loop, right, this clockwise loop, then you can see I will write the equation 3, and my assumed loop is E to F, and the direction of current is also along the same direction, right. So there is no EMF, I will write it 0. So 3 times I1, we will write 3 times I1. Then you see from F, G and G to D here, if you see G to D, your direction of the current, okay, direction of current you will see here, I mean through this resistor, I2 amount of current is passing actually, okay, for this loop. I2 amount of current is passing, but your so direction of current is this, because I2 is entering through this resistor, okay, and your assumption is EFGD, okay, opposite to that of the resistor. So here you need to consider it to be opposite, right. So you got minus 2 times I2, okay. So using this as well, like instead of any 3 combination, you take this 1, 2, 3 equations, or you take 1, 2 and that as 3, the third equation, any three, 1 2 and this one. So any loop you can take and then solve for I1 and I2. Okay, so this way you can find out the unknown. So here we took, like, we took the resistance values here, right, and the potential values are given. So this current was unknown and we can determine solving these equations. Same way they may ask you, the current value will be given to you, potential value will be given to you, they may ask you the resistance, or otherwise they will give you the current value, the resistance value, and the potential here, potential or EMF can be asked to you. Okay, so this is all about Kirchoff's voltage law and Kirchoff's current law or Kirchoff's laws. So try to do more and more numerical problems and try to apply these two laws. Okay, and you can easily solve any complicated networks of any circuit diagram using this. But the assumptions you need to keep in mind, that is, if you are moving from low to high potential, you keep the EMF positive, right? And if you are talking about the potential drop, the direction of current that you considered, and your loop, the direction of the loop, if they are same, you consider positive. If they are opposite, you consider the potential drop to be negative. Okay, and solve. Thank you for watching.